Hello, everybody. I hope you're doing well. Welcome back to a continuation on our dive into least squares. It's so great to be with you all today, and let's plow forward. So, what did we talk about in the previous video? So, in the previous video, I have introduced the concept of least squares and why that problem is relevant to solve, right? But now we want to actually solve the problem, right? We want to solve this problem, right? So, if we have x and y, right? We want to be able to use x to predict y. So if this is my data points, right, I want to be able to find the line that best fits through this data, right, and captures the trend, right? Now, one thing we've discussed in the prior video is that one line can't go through all these data points, right? Usually that's not possible, right? I mean, if you try drawing a line through these 2 points, right, you're going to see that it's only going to go through these 2 points, right? But I can't just curve the line and go like this, right? That's not really the case with how linear functions work. So we have to find one line that best represents the trend in this data, right? So we want to solve this problem, right? And the first step in this problem is coming up with a metric to know how good we are doing, right? Like if we found a good line, right? We don't want to have a problem where we have a line of the form y equals mx plus b, where m is the slope and b is the y-intercept. We don't want to be able to tediously test all possible combinations of m and b, and then hopefully see the line that kind of best visually fits, right? That might be a little bit tedious. And also we want to be smart in what values of m and b we are choosing, right? Because we want to be able to solve this problem with, larger sets of data, not just with 4 data points. What if I had like a million of these data points and we want to fit a line? Then manually testing m and b would be very time intensive and very tedious. So we want to have an algorithm to figure out what is the best value of m and b that'll give you the line that best represents the trend in the data. And to do that, we need to come up with a metric or a gauge to know how well we are doing, right? So let's think about it this way. Let's brainstorm a metric. And the way we're going to brainstorm this metric is thinking about what do we want in a good line, right? So in a good line, what do we want ideally, right? Well, we want the trend to be captured as close as possible, right? So we don't want a line like this, right? In green, right? This line, well, it captures the general trend of the data, whereas as x increases, y increases. But we're not really working with the data, right? This is kind of off center, right? From the data. So that's a major problem, right? And we also can't have one line go through all these data points, right? It's just not possible, right? Because one line goes through 2 points in this case, right? And we can't just curve the line just like that. So what do we want instead, right? Well, we want the line to be as close to each of these x's as possible, right? So what do I mean by closeness? Well, I want this distance here and this distance here and this distance here, right, in green. I want these distances to be as small as possible. Because what does that mean? It means our line is lying as close to as many x's as possible. Let's draw this in a little bit of a better picture to formulate what I mean. So we have x-axis and y-axis, and these are our data points. So here's a line that will kind of pass through this. So what we want is this distance here to be very small, this distance here to be very small, this distance here to be very small, this distance here to be very small. And what do I mean by this distance? I mean the vertical distance, right? So I want these vertical distances right here to be all very small, right? But what else can we do to say this alternatively? If we want all of these vertical distances from the data point to the line to be as small as possible, well, we could just say that the sum of these vertical distances needs to be as small as possible. So we want to minimize the sum of vertical distances, right? Because if we can minimize the sum of these vertical distances, right, then we have found a good line that is best capturing the data. Now, let's define what I mean by a vertical distance, right? So let's go through a bit of terminology, right? So we know that every line has y equals mx plus b, right? This is the form of any line, right? And suppose we had this data point, right? X naught, comma, y naught, right? So y naught is the real y value, right? So when we plug x naught into this equation for the line, right? What is our approximated value for y? Well, when we plug x naught into here, right? Our approximated value for y, which we call y hat, is going to be m times x naught plus b, right? So the line is saying that for x naught, the y value predicted will be mx naught plus b. But we know that the real value that corresponds to x naught is actually y naught. So the vertical distance, right, is going to be simply the difference between this real y value here and our predicted y value. So it's going to be basically the y hat, which is our predicted y value, minus y naught. And we could take the absolute value so that we don't worry about negative distances. So this expression will give you the vertical distance between y hat and y naught. Now, this is a good start, but there seems to be a problem here, right? So we see that when the distance between y and y naught, or this difference, gets really big, I think what might be a good idea is maybe we want to penalize large differences a lot, right? And also, usually absolute value isn't very good in optimization problems. And we'll see that in the later video as to why we don't want to use the absolute value idea. This is not a bad idea though, and this is not a bad distance function, right? So we can simply take the sum of y hat minus, yi, right? Where I goes from 1 to n, assuming we have n data points, right? So we could solve this type of optimization problem, right? But we don't want to solve without an absolute value. And we want to have the power to penalize large differences between our prediction and the real y value corresponding to this x naught, right? So what can we do instead? Well, I'll define the vertical distance this way. So the vertical distance in this case is going to equal y hat minus y naught whole squared. Now, what does this do exactly? Well, we take the difference between the predicted, right? This is our predicted value, right? From the line. And then y naught is the real y value, right? So when we take the difference between the predicted versus the actual y value, we get a difference, and then we square that difference, right? But the thing is, when y hat minus y naught is really large, squaring a large number gives you a very large number, right? So we're essentially penalizing large differences, right? So we want to penalize large differences between the prediction and the actual ground truth. And when I mean ground truth, I mean the actual y naught. So we want to penalize large differences between the prediction and the actual ground truth. And this is what our new vertical distance is going to be. And now what we can do is take the sum of these vertical distances, and this will be our optimization problem. Because as we mentioned earlier, we want the sum of these distances here shown in green to be as small as possible. We've established that earlier. So let's actually flesh this out a little bit. So suppose we have the following data. So we have x is going to be corresponding of x values x1 all the way to xn. And the y values that correspond will be y1 all the way to yn. So basically our data set, you can think about it as x1 comma y1, x2 comma y2, and it's going to be this list of n data points or n ordered pairs. And we want to come up with the function using this as our vertical distance model, right? To model the difference between the predicted value versus the real value. So what do we know from y hat, right? We know that y hat is going to be mx plus b, right? And we know that the ground truth values are here, right? So we take the difference between these ground truth values and the y hat that corresponds for this x. So we want to sum up y hat minus y whole squared. And we're going to sum this up from I equals 1 to n, right? So for a given xi, comma yi, for this ordered pair, right? What do we know? We know that y hat is going to be m times xi plus b, right? And yi is the real value. So we know that the vertical distance, right, vd, is going to be y sub I minus y hat. And then what do we know about y hat? That's simply mxi plus b from the line, right? So this is going to be y sub I minus mxi plus b. So we're going to use that fact in our relationship right here to model the vertical distance. So this expression here that we want to optimize is simply equivalent to doing this. I equals 1 to n. So for each of the n order pairs, we're going to take the difference between the predicted value of y from the line versus the corresponding y value, right? So we're going to do y hat minus y sub I whole squared. And what do we know about y hat? Well, this is the predicted y value we get from plugging the corresponding x sub I, right? The corresponding x value. So this is going to be I equals 1 to n summation, and this is going to be m x sub I plus b minus yi, and we're going to take the square of this difference, right? So this model or this equation shown here in red is what we're going to optimize, right? We want to find the optimal values of m and b, so our slope and y-intercept, that make this value shown in red here, boxed around, make this as small as possible. So we want to minimize. So we're solving a minimization problem here. And this is going to act as the metric by which we use to find the optimal values of m and b. So that's going to be what we're going to do in the next video. Just a side note, this concept is called least squares because we are minimizing the sum of the square differences between the predicted y value versus the corresponding y value. So the least comes from the minimization aspect of the problem, and the squares comes from the fact that we are taking the sum of squared differences and minimizing that sum. So in the next video, we're going to talk about actually solving for the values of m and b. So until next time, I will catch you later. Hopefully, this video kind of gives you a good overview as to the direction we're headed in. So have a good rest of your day.